Hello, my name is Andy Collins, and I'm going to be talking to you today about some research I conducted with my co-authors, Shada Etamade and Pilar Pasalogo. We're from Old Dominion University, which is an R2 state university in Southern Virginia in the United States of America. And what we were doing was a human experiment using a hybrid agent-based model. Strictly speaking, agent-based simulation, but model sounded nicer. So, what we do in this? Why? What's the point? Well, what we wanted to do was we wanted to model some human behavior in the context of strategic group formation using agent-based modeling. Agent-based modeling has been criticized for not including very accurate human behavior, and so improving that ability is considered a good next step. So there was two issues that we faced. The first one is, how do you integrate strategic group formation into an agent-based model without throwing the baby out with the bathwater? And what do I mean by that? Well, if you aggregate the agents up, then you're no longer really using an agent-based model. Okay. The other issue was, do these computerized agents, do they actually react like humans would? So are they reflective of human behavior? So the way we wanted to investigate this was, what we did was we created a hybrid simulation of strategic group formation, and we conducted a human-in-the-loop experiment to see how the human would actually react in the context of our simulation. So what we wanted to do was we wanted to help determine what kind of effects a person's experience might have on their behavior. The other issue we wanted to determine is, was the behavior that the humans demonstrated similar to those generated by the hybrid model? Okay, so the agent-based modeling simulation algorithm called ABS core algorithm governs the simulated agent's behavior. What it does is, during the game, agents are able to suggest and join other coalitions, coalitions being a group of agents. So why hybrid simulation? Why are we doing this? Well, the reason we're doing this is because cooperative game theory is the way of dealing with strategic group formation. However, it's got all kinds of issues. It's normally, you have to solve it analytically, and also if you're trying to solve it just in a simple game with a large number of players, is computationally intractable. So agent-based modeling allows us to produce a heuristic approach to overcome at least some of the computational complexity issues. And why do we need cooperative game theory with an agent-based modeling? Well, agent-based modeling lacks such a strategic coalition formation behavior. Okay, so what we did was we what we call enriched the agent-based model with an heuristic algorithm of finding a cooperative game theory solution. The core is the solution mechanism that we considered. Strictly speaking, the core is a stability criteria, but I won't go into the details here. So we first came up with our algorithm back in 2018, but then we improved upon it, and we've recently come up with a much more efficient version of the algorithm, and it's also more and more accurate. The old algorithm was shown to be not particularly accurate. The new versions hits the core about 96% of the time, so it's a pretty good approximation. Okay. So what do we do? What's the scenario that we use within our simulation? Well, we use a thing called the glove game. The glove game is a standard game using experimentation within the cooperative game theory world. And what we did was we built a simulation of the glove game. We had the humans play one of the agents, so in there, and the remaining agents were controlled by the algorithm. And what happens is each of the agents is endowed with a certain number of left gloves and right gloves. They can sell pairs of gloves, but they can't sell individual gloves. And if they form a coalition, they can pull their gloves together, and they can sell the collective pairs, but they have to equally split the revenue. What does this mean? Well, it means that the players have to balance between how many people they let in the coalition, because they're having to share with them, with how many pairs they can generate. Okay. So there's two types of decisions that have to be made by the agents. One of the decisions is what coalitions they would suggest, and the other decision they have to do is, what coalitions that are suggested to them they should accept. So the data that we collected for this, well, actually we collected a lot of data from this experiment. The one I'm going to focus on here in this presentation is the data to do with consistency between the human players and the computerized agents. So what do I mean there? So given the decision that the human player made, was that possible or viable by the computerized agents? Okay. So, for example, if there was a decision to join a coalition offered to the player, would the computerized agents have made the same decision? Okay. Similarly, the other way is if when they suggest the coalition, would the computerized agents be able to have suggested that coalition? There's a stochastic element to the simulation, the stochastic element to the algorithm. So it doesn't necessarily mean they would have suggested that simulation, but could they have suggested that simulation? That coalition. So this is just a quick overview of the trial protocol. We did a prototype and we discovered that even though by cooperative game theory standards, a glove game is a very simple game, it's quite confusing to the novices. As a result of that, we had to include a much longer testing and teaching period. They actually go through 5 games, teaching games and testing games to start with before they reach the 2 main games that we're actually collecting data on. The first 2 training games are actually done with an instructor showing them. The next 3 are done using the interface that they will use. And then finally, the last 2 games are the actual games that we're considering. Okay, we had 2 different types of games. So one thing I didn't mention about the core earlier is the core of a game isn't guaranteed to exist. And if it does exist, there could actually be multiple elements of the core. An element of the core is a coalition structure, a partition of the agents that satisfies the core stability criteria. Okay, so we considered one game which has only got one single solution, and we considered another game which got multiple solutions, just to see where they ended up. So this is just given a flow diagram, decision diagram of what happens during a round. Effectively, it's the suggestions and acceptance by the different agents, and it keeps looping and looping around this each iteration until eventually the human player says they are satisfied with the current state of the game. So just to show you the actual interface that we used, I'll show you a game here. We've got 7 players. The human player is player 0. We hit go. The human player can then make some selections. So it's got 1 glove and 3 right gloves. So maybe going with number 5 is a good idea. Click himself as well. I was happy with selection. Oh look, they formed a coalition because their colours have changed. So the grey indicates the colour, so they're 0 and 5 are in their coalition, and so is 1 and 2. And then we can repeat doing this. We can keep going, and then suggestions may pop up from the other players. Okay. We conducted a variety, or actually 31 different trials. Here's just a diagram of my 2 co-authors demonstrating what happened in the live version. COVID hit halfway through our experimentation. We had to convert to an online version. We did some testing, and there doesn't seem to be any impact on the results from that. So there were 31 people that were involved in this. There were a lot of different demographic information we collected, but it had no effect effectively on the results. The one that did seem to have an effect is experience with board games. Approximately 13 out of the 31 players had experience with board games. We'll talk about those results in a second. So the demographics are very split, as a spread over the population. There is a bias towards people with higher educational backgrounds. It's not unsurprising because we work for a university. People we tend to have the higher degrees. Okay. So our main research hypothesis from the paper was this idea that board game experience does have an impact, and that people with board game experience tend to act and decide more like simulated agents than humans with no experience. And what we did here was this shows the percentage of time of consistency between the two groups. It is statistically significant. Just wanted to point out we're not talking 31 decisions here. We're actually talking over 200 and 256 decisions that were made over the courses of all the games. These are then broken down. Now, there's some issues with the fact that there's some of those decisions made by the same person. Therefore, there's an interdependency. But if you ignore that, you do see there's a significance between those that have board game experience and those that don't. So two things to draw away from this are there does seem to be a high level of consistency between the agent's behaviour and human behaviour, and people with board game experience tend to be more consistent. Now, another result I wanted to show you was the difference in the reward obtained. So we only found about 40% of the human players, or the human played games, that actually resulted in the core. This was quite disturbing initially, but then we investigated a bit further. So this is the game with multiple possibilities for the core. And on the left, you can see the payoffs, the rewards that were obtained by those players that ended up in a core coalition, a coalition that is in a core structure. Okay, so what you'll see here is that the majority of the players only got a reward of 1.5, and there was a few that managed to get the maximum value, which was 2. Now, what's interesting about this is that the majority of players that were in the core coalition managed to get a reward of 1.75, so they tended to beat those that ended up in the core. What happened there was they were actually taking advantage of a particular loophole in the game design, which was there was the slowness of the computerized agents to react to the changing coalition structure. So if the player played for a bit, got happy with their 1.75 reward, then pretty much could finish the game. So I thought it was quite interesting the fact that the humans were able to quite regularly break the game, with a few exceptions. The one that got the very low reward there, just to let you know, they would constantly just they wanted to be with one other agent that kept rejecting them, and they keep trying to ask them to be in a coalition, and then in the game they just got frustrated and then quit the game. So conclusions. So the results indicate there is a slight difference between humans and simulated agent behaviour. So it's something we would need to take account of, and I've got some ideas of how we might approach that. This difference is for lower with players that regularly play board games, which was expectation. The results did confirm that humans were consistent with the simulated agents the majority of the time. Okay, which is good. Which is a good indication that our algorithm is an approximation that we can use for doing modelling strategic group formation. No other demographic information affected the human's behaviour, which is interesting. But there was a noticeable difference on the final reward depending on their outcomes. Okay, so the next stage for us now is actually to do something a bit crazy. So we had a computerized simulation which we removed one of the players and replaced it with a human. Human lives experiment, which we just discussed today. What we're going to do now is then replace that human with a computerized agent, and then compare the results from the computerized agent playing as a human with the human player, and see if there's any differences there. Okay, so now we're going to move over to the question and discussion section on the website. Okay, thank you for your time.